The topic of this lecture is short method of finding particular integral wherever qx is a polynomial. We will cover these points in this lecture. F dy is equal to qx. This will be the expression where qx is a polynomial, and we'll see these three examples. We'll cover these three examples in this lecture. So consider the general nth order linear equation of the form f dy is equal to qx, where fd is having this form where d represent d by dx, that is derivative with respect to x, where the coefficient a0, a1, a&r these are the constant. For certain particular forms of the non-homogeneous term qx, that is this one, in the above equation, there exists short method of finding particular integral, and we'll see one of the method wherever your qx having the specific expression that is of the polynomial. So the task is explain the method of finding particular integral when qx is a polynomial. Okay, so for the solution, let ft be a polynomial in D of degree n. So what we are supposing that this fd is a polynomial in degree d, and qx, that is a non-homogeneous term, is a polynomial in x is of degree say k. Then consider the equation f dy is equal to qx, then pi is given by, we know this is given by yp is equal to 1 upon fd into qx. Now let us first assume that d is not a factor of fd. That is, there is a no factor d in fd. That is, fd is having polynomials, so some expression will be there, but d is not there. In this expression, d is not separated. That is, this into d does not happen. This is not the case. So we then arrange fd in ascending power of d, and we divide 1 by fd until a quotient of the form c0 plus c1d c2d square plus ckd to the power k is obtained for constant ci's, and a remainder involving powers of d higher than k. That is, we are going to start divide 1 with fd, and we'll get these types of expression. So this will be as a quotient, and the remainder will be involving powers of d higher than k. This will be clear when we'll see some examples later on. We have written the quotients only up to the terms involving dk. Why this is so? Because qx is a polynomial in x of degree k, and higher order derivatives would yield 0. The value of that will be 0 when applied to qx. So now if we write the remainder in the form dk plus 1 gd for some polynomial gd, then we'll have 1 upon fd qx. So this is the form which we have obtained. 1 upon fd, this is becomes this expression that as we have seen in the last slide, into qx, and this is the remainder term divided by fd, because this can be written as 1 upon 1 is written over here. When we divide by fd, we get expression. This expression will come over here. This expression, this comes over here, and then when we write this 1 upon fd, this will be written in this way. This expression plus this expression, and qx is operated on both. Now since the second term vanishes on applying qx, this term will vanish. This term will become 0. So we have yp is equal to c0 c1d plus c1 plus and so on ckd to the power k qx. Now let us assume, so this is the first case. Now let us assume that d is a factor of fd of order say h, where h is less than n. Then how will write fd? Fd can be written as d to the power h into some gd, where gd is a polynomial of degree n minus h. Then 1 upon fd can be written as 1 upon d to the power h into 1 upon gd. Thus 1 upon fdqx will become 1 upon d to the power h into 1 upon gd into qx. We then proceed with 1 upon gd exactly as the above to compute the particular integral. This will do as we have done in the last slide. So and then we'll apply this. This will be nothing but the integration h times this types of integration will be there with respect to x. In either case, the method is this is the important. The method is to express 1 upon fd into this form, that 1 plus polynomial n d to the power minus 1, and expand using the binomial expression. Now these two are important formula which we will use in when we'll solve the question. 1 minus x to the power minus 1 is 1 plus x square plus x cube and so on. And 1 plus x to the power minus 1 is 1 minus x plus x square minus x cube and so on. So by this way this method is explained. Now we'll see some examples. So this is the first example. Here find the particular integral of this question. Now here pi, particular integral, this will write 1 upon 1 plus d square plus d cube, because this expression can be written as this should be d cube. So d cube plus d square plus d into y is equal to, on the right hand expression. So this becomes, we'll write like this, and here it is in the ascending powers of d, it is already in this power. So this can be written as simply as 1 plus, this can be written as 1 plus d square plus d cube in one bracket to the power minus 1, and using the expression which I have told in last slide, 1 minus x to the power minus 1 becomes 1 plus x square. So using this we'll expand this. So the first term will become here 1 minus, because this is plus is there. So in case of plus, what happens? This becomes minus plus minus plus. So 1 minus x, 1 plus x to the power minus 1. If this is the case, then this is 1 minus x plus x square and so on. So using this, the first expression will come 1 minus d square plus d cube, then plus d square plus d cube square and so on. So this, when we'll expand this, we'll get this term. And when we'll operate this is what is d? D is simply, we know this is d by dx. What is d square? D square is second derivative, d2y by dx square. d2 by dx square. So when we'll operate this on this expression, we'll get, and when we'll solve this we'll get this expression, and when we'll simplify, we get this expression. So by this way this question is solved. Let us see one more example, you will get idea. This pi, this question we have to solve. This is your pi, we'll write like this. Now when we multiply by 1 minus d on in numerator and denominator, because of this whole expression will become 1 minus d to the power minus 4. So this is written in ascending power of d, and this 1 minus d will be operated inside. So this expression will become simply this, and this expression 1 upon 1 minus d to the power 4 becomes 1 minus d to the power 4's inverse. So this will simply will become 1 plus d to the power 4 plus d to the power 4 square, that is d to the power 8 and so on. So this expression is written over here, and when we'll operate this on this, we get this expression, and on simplifying we get this expression. So that is very easy in this case. Let us see one more example. Solve d cube plus 3d square plus 2dy is equal to x square. This is auxiliary equation, this is complementary function. We are interested particularly in particular integral. So yp is like this. Now from here we have taken common 1 upon 2d. Why this is so? Because now this expression becomes in the ascending power of d, and this will become then 1 upon 2d as it is, and this expression can be written as 1 plus 3 by 2 d plus 1 upon 2 d squares inverse. So this becomes, and when we'll open this becomes this expression, and when we'll apply x square inside, we get this expression, and on solving we finally get this expression. So by this way, these types of question can be easily solved. You can try these questions. These questions are very easy. Thank you very much.